In this video, we're going to discuss the concept of heating curves and phase diagrams. But to start with, we need to go over some vocabulary. So first off, we want to mention some terms that you may or may not have heard of. So we've got the word sublimation and the word deposition. So I'm going to assume, for example, that you've heard of the word evaporation, for example, where liquids go to gases, which we can also call vaporization. You've also probably heard the term freezing, where we take something from a liquid and go to a solid state. There are a few terms that you may not have heard, or you may not realize exactly what they mean. So we're going to go over a few of them, and there's one more after this. So sublimation, when I find my marker again, there we go, is the process of going directly from solid to gas. And we'll get a better idea of this when we look at what a phase diagram is. But in general, the concept is that some substances aren't going to go through a liquid phase under set conditions. The most common example you may be familiar with is carbon dioxide. Carbon dioxide can be sold as dry ice. Now, if you take dry ice, and let's say you buy it from a grocery store because you were going to do a volcano experiment when you were a kid and you wanted to be able to show it off, or just you liked the fog from it, you had some use for it. What you'll notice is it doesn't ever become a liquid. At atmospheric pressure, it goes directly from solid to the gas phase. That process is called sublimation. We can also get the reverse. That's what deposition is. That's going directly from gas to solid. Now, there's one other term which you may not have heard as much. So, generally, when we talk about a solid going to a liquid, we're going to talk about melting is the term we'll use. I'm not going to be too concerned about why, but in this class, we're going to call that fusion sometimes. So specifically, this means that when we talk about the enthalpy delta H of fusion, that is referring to the amount of energy when I go from the solid to the liquid state. Let me check something real quick. There we go. Yeah, just making sure my recording was actually going. Didn't want to have to re-record all of it. So when we go solid to liquid, the amount of energy that takes, that is involved in that transition, is going to be called the enthalpy of fusion. Some other things we want to note is that just like we talked about with vaporization, delta H of fusion, enthalpy of fusion, is always endothermic. So what that means is when we go from the solid phase to the liquid phase, is our system is going to take energy in to do that. It takes energy from the surroundings that is going to go into the bonds to be able to do this, to get it to make this transition. In general, delta H of fusion, so write this down, is usually going to be less, and probably significantly less, than delta H of vaporization. So this is usually true. The other thing to note is that we know that delta H of fusion is going to be the opposite of freezing. So if we change the sign, we get this. Just like when we talk about vaporization, we know that delta H vaporization is going to be the negative of delta H condensation. So a lot of times what will happen is you'll be told one of these. Like if you look them up, you'll look up delta enthalpies of fusion or enthalpies of vaporization or enthalpies of sublimation, and then you would just have to know, oh, the reverse version is the negative version. And as delta H fusion, that fusion process is always going to be endothermic. That means that our freezing process is always going to be exothermic. So those are the terms I wanted to get through. Now let's talk about something we call a heating curve. So the idea behind a heating curve is you'll see it, and it'll tend to have these units. We'll have energy, probably in kilojoules. And this is going to be energy added, or it might be said as heat added. So I'll see it as heat. I think that word's a little more likely there. And it'll probably be reported in something like kilojoules per mole. Doesn't have to be exactly kilojoules per mole. You could do it in joules. Or for a specific sample, it could just be kilojoules. Kilojoules per mole, so it's a generic curve that would apply to any sample. Now I'm going to try to write sideways. It's not going to work. Okay. So I'm just going to write it like this. Temperature, trying to write sideways on my tablet is hard. And that's probably going to be in degrees Celsius. Could be Kelvin. So what happens is this is the way we're going to report what occurs when you add energy to something. So let's take an example, and your textbook has an example of ice. You can go look at ice going all the way to steam. So we have an ice cube my attempt at an ice cube. So ice is going to have to start at a temperature of 0 degrees or less. So let's say we start at, let's say, negative 20 degrees Celsius. That's going to be the beginning. So I'm going to make a dot here that represents our start. And that's going to be negative 20 degrees. Now when we add energy, what's going to happen at first is what you might expect. Hey, we add energy, temperature goes up. This matches generally what we think about when we add energy to something. That's how we make things hotter. Oh, and I blocked it, but it just says, let's say, we'll keep that on there. So we're negative 20 degrees. We start adding energy. That's going to heat it up. Now, eventually, we get to 0 degrees. What's going to happen here is this is our melting temperature or our temperature for fusion. So now at 0 degrees, what's going to happen is for a while, the temperature's not going to change. But this doesn't mean that nothing's changing at all. Instead, what's happening here is a phase change. At the beginning of this, everything's ice. As you add energy, the ice turns into liquid water until you get to the end and all of it's transitioned to liquid. Remember, we said that going from solid to liquid is going to take energy. So all the energy added is going into that phase change. Then once it's all turned into a liquid, temperature starts going up again. And it keeps going up, and we get to 100 degrees Celsius. Remember, 100 degrees is going to be our boiling point. So just like we saw with solid to liquid, liquid to gas takes energy. So our energy goes into phase changing, and our water is starting to boil and turn into gas. But what you'll notice about my drawing is, hey, look, it looks like I'm just going to keep going and going, right? The enthalpy of vaporization is a lot larger than our enthalpy of fusion for water. So it's going to take a lot more energy to get it to transition. But eventually we've had enough, and then it starts going up again. So this is our phase change again. And this time it is from liquid to gas. Okay. So that's how we pictorially represent what's happened. We'll also look at some problem solving in a moment, but I want to do one more picture related thing, and then we'll do a problem with this. Like, how do we take all this and then use information like the enthalpy of vaporization, the enthalpy of condensation, the temperature change to figure out how much energy this actually takes. So, there we go. Back to that. I lost my pen. There we go. It's back. So the one other thing I wanted to mention is something we call a phase diagram. So when you see a phase diagram, it might look something like this. Okay, I'm just going to start over because I'm drawing. I was having trouble with drawing. We're just going to start over. And, down at the bottom is going to be temperature. And on the y-axis, you pressure. Now, when you see these, not always, but many of the ones in textbooks at least aren't going to be drawn to scale. And that's because some of these things, it just doesn't look, if you see one to scale, what happens is they'll be really hard to see certain parts because there'll be really small temperature ranges where certain things are true. So they give you an idea and they'll make sure to label numbers that are important on them so you can still use them. But do understand that they are not necessarily drawn to a linear scale like most of the graphs we do. So I want to bring that up because occasionally things might look weird. So we go here, we get to a point, and then we start going this way. And that just keeps going. We have another line that goes like this. We have a point somewhere. Now, so far, this doesn't need to mean anything if you haven't seen one of these before. So what we do with one of these is we divide our substance into 3 phases. So down here at the bottom, I have got my thing at my pressure. One second, I'm going to make sure I drew the line in the direction I wanted to, right? Where is that? Yeah, that's how I wanted to draw it. I was making sure I had the direction of the curve I wanted, and I'll talk about that in a second. So we have gas over here. This is going to be a solid, and this is going to be a liquid. And these lines divide this up. So what that means, if we take any temperature and pressure and we plot it on this graph, we'll land somewhere. So for example, let's say I took a temperature and pressure, and I landed at this dot A here. Well, that dot A is a gas. because it's in the section labeled gas. Now let's say I were to take that gas and I were to cool it down. I start cooling, and hey, eventually I get to this point here, point B. This is along the line separating the gas and the liquid. That means point B represents a point where condensation would occur. So at B, I can have liquid or gas. But then if I keep going, and let's say I start in the middle here, I don't have we're going to try to draw a C there. Point C is going to be just liquid. Then if we keep going, we'll make a new dot. I'm going to call it D. I know they're close together. That D dot is going to occur between the line between liquid and solid. That represents our freezing point. So then it's going to freeze, and so it can be either liquid or solid there. But if I keep trying to drive the temperature down, eventually I'm over here, and I'm just solid. Now some things to notice. Let's say we started at a lower pressure down here for gas. Well, if I kept going, I'm going to go to this point here, and I'm going to transition straight to solid. So that's going to represent deposition, a gas to solid transition. There are a few other terms to mention about this curve. You notice there's one dot that occurs in the middle where solid, liquid, and gas are all at the same place. This is called the triple point. There is a specific pressure and temperature where all three phases can coexist if you existed exactly there. The other things to note is these curves can have some names. So for example, initially the curve, when you first start drawing it, is separating the gas and the solid. We call that the sublimation curve because it's the curve where if you're anywhere along that, you're at the point where it's ready to sublimate or deposit if it goes across it. Then once you reach the triple point, it's going to split in two. The arrow going up, like this one is going to be a separation between liquid and solid. So we can call that our liquid, solid to liquid. That's our fusion line, because that's going to separate either fusion or freezing. Then the other line that went up, that's going towards this dot here, which we'll talk about in a second that I just circled, that line's going to separate liquid and gas. So that'll be our vaporization curve. That'll separate out the gas going to liquid or liquid going to gas. So either vaporizing when it goes to gas or condensing when it goes to liquid. Now you see this point here I circled. This is something called the supercritical point. What happens here is once your pressure and temperature get beyond that, so if you're in, I'm going to draw a box here. So if you're anywhere in this region here, that you're going to be instead something called a supercritical fluid. And what happens there is there's no longer a distinction that cleanly goes, oh, this is a liquid, this is a gas. It has some properties of both, and it's not going to try to separate between them. So once we get there, we don't have that separation. On the other hand, that line between solid and liquids, you notice I drew an arrow on it. That's because it just keeps going. There isn't going to be a point where we go, oh, this is no longer a separation between solids and liquids. Another final note, these are the most common phases we work with. Depending on the particular substance, you can have other types of phases. Phase diagrams can get more complicated. For example, some textbooks, and I think the one I'm working with right now does this, they have a problem where they show you that if you have solid water, once you get to really high pressures especially, there are a bunch of different phases of ice. So it'll show you different ones. Like, oh, if you cross this barrier, you go from ice 1 to ice 3. Then ice has slightly different properties between those. So there are still phase transitions. So we can do phase transitions other than solid, liquid, gas. But on the first phase diagrams you see, they're probably going to be like this. Also, when they're drawn this way, gas, solid, and liquid aren't always labeled. You're expected to know that gas is going to be the one that's going to be at those low pressures, and as temperature goes up, that solid's going to be up on the left like it is, and liquid's going to be where it is. You're expected to know those just from looking at a couple of lines on it. I'll show you an example of that in a moment, of what a problem might look like that. So that is assumed that if there's not specific labels, that's what you should assume. And you will eventually, if you stick with us in science, depending on what areas, especially if you do things like materials science, you'll start to look at materials where you're interested in phases other than just solid, liquid, and gas. And you'll learn about how those exist. But we're going to stick to the solid, liquid, gas, supercritical fluid for our discussions. Now, let's now do some problems. So I'll do one of each. I'll do one of the phase diagram, one with our heat curve. So this is an example of how we could word a problem for a heating curve. So let's say we have a 25-gram sample of acetone, and we cool it from 20 degrees to negative 110.8. And I want to know how much energy is lost by the sample during this transformation. What our goal is to identify what phase are we in at the start of this process, what phase are we going to be at the end, what points are there phase transitions, because we have to break the problem up, because you can either heat or cool, or you can change phase, but you're not going to do both at the same time. So this problem is going to be multiple steps. It can just be one if there's only a phase transition, only a temperature change. But in this example, starting at 20 degrees, that occurs between the melting and boiling point. That means that this substance starts as a liquid because it's in between those two. And negative 110.8 is below the melting point. So that means it's going to go from liquid to solid. So we break the problem into 3 parts then. So from 20 degrees to negative 94.8, that's step 1. That's going to be liquid cooling. Then we're going to phase transition. So this is step 1. Step 2, liquid to solid transition. And then step 3 is going to be negative 94.8. I didn't give myself enough room. Negative 110.8. I'm just trying to give myself the authentic student experience because I've definitely done this when I was a student. I'm like, okay, I've just got a little bit of room. Let me squeeze it in there. And so this is the solid cooling. So we have to solve each of these steps separately, and then we add all the energies together that are either lost or gained. Now this one, we're cooling something down. So there are going to be negative values because the temperature is going down. A lot of examples in your textbook and problems you'll see will be heating things up. Then they'll be positive. I'm purposely doing a cooling example because I see so many heating examples that sometimes when people see the other one, they go, oh wait, how do I do it that way? I just learned the first one. So first for cooling, this is similar to what we did in 1211. And we talked this a bit earlier in this chapter. Q equals MC delta T. We're just changing heat, no phase differences. So here, we want to know how much energy is involved. We have 25 grams, and that's not going to change anywhere in this problem. Then we have a specific heat. So for the liquid, the specific heat is 2.15 joules per grams. And I'll point out, for these problems, don't worry about whether it's Kelvin or Celsius as long as you keep it this. You don't change it in the middle of some transition you're doing. We're not going to worry about why, but basically delta T's, if you calculate them using 2 Celsius temperatures or 2 Kelvin temperatures, you get the same thing because you're taking a difference. So here it's K, you'll see C a lot. They do indeed cancel in this instance, so I'm just going to go ahead and write C here. And we'll just treat these like they're C because that's okay. It doesn't change anything here. That is not true if it's not a difference. It's because you're taking a difference. That's why I can say the Celsius and Kelvin are similar. If it were not a difference, then I would have to convert to Kelvin or convert to be able to do the problem. So here, my temperature difference. So my final temperature for the cooling, remember this isn't the whole thing, it's just the cooling, is negative 94.8 degrees Celsius. I'm going to subtract the initial, that's 20 degrees Celsius. So those combine to give us negative 114.8 degrees Celsius. So we're going to take all this, let's multiply it all out, 0.15 times negative 114.8, and I'm going to get negative 6,170.5 joules. Note, I'm only going to have 3 sig figs in my final answer, but I'm going to keep a few extras as I go so that I don't have any rounding issues. To not have to worry about that, I'll deal with rounding at the end. So that was step 1. Then step 2 is a phase transition. So that's going to be Q, and we're going to take the number of moles times delta H, in this case of fusion, because we're going from liquid to solid. Oh wait, just kidding. Not delta H fusion. This should be our delta H. It's going to be our melting. Freezing. I know what word it is. It just takes me a minute. I was just checking with you. Yeah, no, it's going to be the enthalpy change of freezing. Now, the reason I have it in there is because this delta H is listed as kilojoules per mole. You will sometimes see versions listed in kilojoules per grams. That would also be possible. If that were true, you would instead use a mass in this equation instead of a number of moles. Both are fine, but you have to make sure the units work out, so use the units you're given. So since I need it in moles, I need to do a quick transition. So I have 25 grams of acetone. I got to find the molar mass. I just realized I didn't write that down, so I've got to calculate it myself real quick. So the molar mass for acetone is 58.09 grams per mole. Mole of acetone. That's supposed to be a 6, CH6. So we take 25, divide it by 58.09. We're going to get 0.4304. Again, I'm saving an extra sig fig. I wouldn't need quite that many, but just to make sure I don't have rounding problems. We have Q equals 0.4304 moles. And then I'm going to multiply it by negative 5.69 kilojoules per mole. I'm doing negative because they gave us fusion, but we need to use freezing. And they are the opposite signs, but the same value otherwise. So we just put a negative in front. So when I multiply those out, I get 0.4304 times negative 5.69. So that here, Q is equal to negative 2.449 kilojoules, or negative 2,449 kilojoules. Or joules, sorry. I'm going to go ahead and convert it to joules. When you add these together, they've got to be the same unit. So if you don't make that conversion, you're going to get an answer where 2 almost didn't matter, because if you add 6,170 and you add 2 to that, it doesn't really change much. So make sure to watch your units. So then we have step 3. To make sure there's room. My face is going to disappear. Bye, I'll see you back on the next slide. So for 3, we again have Q equals MC delta T. But now we're doing solid cooling. So Q is still going to equal 25 grams. We haven't changed anything about the mass. But our specific heat is now 1.65 joules per grams degrees Celsius. And then our temperature difference, well, our final temperature is negative 110.8 degrees Celsius. And then we're going to subtract a negative, which means we're going to add our 94.8 degrees, which is where we were at our melting point. So yes, it's minus a negative. That's why I put a plus there. So we do that, and if we multiply all these numbers together, we're going to get that our energy for the solid is going to be negative 660, so I don't have anything else to write. That's this one. I'll put 0.0 joules. So that's the energy that it lost as it went from negative 94.8 to negative 110.8. So the final answer we want, so Q total is going to be equal to 1 plus 2 plus 3. We could also say Q1 plus Q2 plus Q3. So we add all those together, negative 6,170.5 minus 2,449 minus 660. I'm going to get, and I'm going to round it now, negative 9,280 joules. So this is the amount of energy lost by our sample of acetone if it's cooled from 20 degrees to a negative 110.8. This may not always be the exact set of phases you change in a problem, but this is the strategy for it. So what you have to do is you have to notice what's your melting point, what's your boiling point, and that'll tell you what phases you're in, so which types of transitions you're doing. You then need to also pay attention to what phase change you're doing. For example, if this problem had looked at liquid going to gas, that's vaporization. Then you need to use the delta H of vaporization, not the delta H of fusion. You might also have a problem where you could go all the way from solid to gas, and then you've got a 5-step question. You've got to do 3 different temperature changes. You've got to do the solid, the liquid, and the gas heating up or cooling down, depending on the order, the direction you're going with temperature. And you have to do 2 phase changes, a solid to liquid and a liquid to gas. So it just depends on the problem, how many phase changes you'll have to do and how many temperature changes you'll have to do. And you have to base that off the melting and boiling point you're given. Also make sure you use the right specific heat. They are different for the different phases of a molecule. Now, let's look, you didn't need to see my whole face there. Let's look at a problem like this. This is how we can ask a question about a phase diagram. Let's take this thing and let's ask what phases are present at point F. So based on what we discussed at phase diagrams earlier, I want you to give this a try. So what did you come up with? Did you come up with the fact that there was gas and liquid both present at F? If so, good spot. If not, I would go back and look at the earlier part of the video where I go through those phase discussions again about what each of the ones represents. Also want to use this to draw like how phase transitions, what they might look like. So for example, you might ask, well, what if we went from B and then we decrease the temperature? Well, if we decrease the temperature, it's going to go from liquid to solid, but it's never going to turn into a gas when you're doing that. You could also be asked a question, like let's say we're at point A, and A is at a set pressure and temperature. And if I asked you, if I only change the pressure, can I turn that into a liquid? And the answer is no. So if we look, and I were to draw a line for pressure change, it would go up and down, and we could go solid to gas. But we cannot go solid to liquid. It never crosses that line. Now, if you were instead asked what temperature changes, A can do all three at this pressure because it crosses the solid liquid line and then again crosses the liquid gas line. So point A, if you change the temperature, could go from solid to liquid to gas. But if the temperature remained constant at point A, you could only go from solid to gas by decreasing the pressure. So the goal of these types of problems is just to read the graph really and see, okay, how can I move around on it? And it's making those transitions, which is one of the best places to ask questions, but also not thinking about tests, just how you use this. That's what's useful about it. I can look at my material and go, okay, if I'm at this pressure, like I'm always going to work, let's say, at 1 atmosphere. What are the properties of my substance? What are temperatures going to do to its phase? When does it change? Does it ever become a gas? Does it ever become a liquid? Does it ever become a solid? Or am I going to need to increase the pressure somehow if I want it to be able to do one of those things? That's the type of information you get out of your phase diagram. So hopefully that helped out, and this concludes our intermolecular forces chapter. If you're continuing with my videos, we will be moving on to solutions next.